One of the big growth drivers of data, which is still exploding at a tremendous rate, is the Internet of Things. And as this Internet of Things takes off and these devices start sending data either back to a company that's managing them or into the public cloud, that's going to cause some issues, right? You have to be able to process the data as it's coming in, extract the information that you need to make decisions on, and then keep that data around for the analytics software that's going to actually make decisions on behalf of what that data represents. In some cases, you're going to need to keep that data around for a very long time. And it may not be frequently accessed since you've already extracted the information you need, but when you want to go back and do historical research, you want to know trends across time, you still need to have that data around. You just can't throw it away. It's very valuable to the corporation, and the analytics is going to require it going forward. That is going to change some of the architectures. What does it mean for cold data, for cold storage? Does that need to be even cheaper because you've got such huge amounts of it, right? What does that mean for the active data, the data that the analytics is working on? Does that have to be faster and faster? Things like persistent memory are going to affect that. So you may see a trend towards more persistent memory use as we work out the infrastructure changes needed to accommodate that. But we also may see stuff on the other end, optical drives getting cheaper, longer term. 100 years is not an unreasonable number to keep some of this data around. There's a spectrum of offerings out there, from public cloud to private cloud to hybrid clouds that blend the two concepts and processes together. And some businesses don't need all of their data in their own private cloud. So they may be looking at a hybrid approach where the appropriate data lands in the appropriate place. Some of it will be in the public cloud, some of it will be in the private cloud. And then the issue is, how do you compute against that data? You don't want to be moving large amounts of data around between the public and private cloud. So the way to solve that is to do the compute close to the data. This is called data gravity. In other words, don't move the data, move the compute to where the data is. Then you get a very low latency, very quick response time, and you can solve the problems where the data is already in place. So the data acts like sort of a large mass that's collecting other large masses around it, just like gravity is, and that causes some changes in architectures in order to accomplish that. There's been an issue with clouds being trusted. And if I put my data in a cloud, whether it's private or public, how is it secured? Who has access to it? Can the administrators get in and look at my data? If so, could that leak? Could the administrator password leak? And then you get a data breach. But there's also physical security concerns as well. How is the data center secured? Who's allowed into the data center? The physical drives that are leaving the data center, how do you get the data off them in a secure manner? A lot of companies and a lot of public clouds are shredding their disks before they leave the data center, right? And if that is a disk that's still under warranty and it's being returned to the drive manufacturer, what the drive manufacturer gets back is a pile of dust. And yet they still have to ship a replacement drive. So if we can get it so they can trust the secure erase mechanisms, we'll get it back a drive that can be analyzed for why it failed. Otherwise, they're going to continue shredding the drives as they leave the data center, and that doesn't help anybody.